I built these 25 edge clamps because buying 25 of these is a little expensive.
Oh.
I needed them for a furniture project, and as their name suggests, they clamp stuff to an edge and automatically adjust themselves to any thickness up to 45 millimeters. Pretty cool. I thought this would be a quick side project, but I was so wrong. Dipping my toes into the production world kicked my butt. And forehead. We'll get to that. I had to think differently when designing these, because everything matters when you have to do it 30 times. Wait, 30 clamps? Yes, I will give 5 of them away to one of you. More on that later. Now, let's engineer some clamps for a small production run. It starts with the frame, which needs to be strong, because as you tighten the screw, the eccentric cams try to spread the frame apart. It's interesting to compare my design to the commercial one. They've used a single cast aluminum part. Perfect choice. Now that's no option for me, so I have a hardwood C-frame, and to make this strong it needs proper joinery. Like a mortise and tenon, or a double mortise and tenon, or a bridle joint, or a finger joint, or scrap the whole hardwood and make it from plywood. But which one is the strongest? I don't know, so let's find out. I made 2 samples of each option as an almost finished C-frame with most of the features. But since my best measuring equipment is a suitcase scale, for the actual testing I called in the expert Matthias Wandel and his joint strength tester.
My tester has this motorized screw jack which sits on some load cells to measure the force, and that lifts up on this side, which pulls on the clamp frame until it breaks. First one is a regular mortise and tenon joint. It's 50 kilograms now. Definitely seeing quite a bit of flex there now. So it's opened up by this much. Okay, whoa! Now the failure wasn't the joint at all, it was just the wood right here. Next up, a bridle joint, and I want to see better how much this flexes, so I'm just going to stick this piece of wood in here. That'll make that more obvious. 90, 100, and you can see it opened up quite a bit already. 125, and we broke the wood again. So these more complicated joints, like a double mortise and tenon joint, aren't going to help any if the wood breaks. But we've got 2 plywood samples here which are not going to split apart on the end, so I'll try those next. 70 kilograms now, and we can see it opened up a fair bit, so there is some kind of flexing in the wood already. 170, man, that's a lot of bending. Holy crap, that piece is so bent now. 230 now. I just hope I don't break my test setup. 275, okay, something, come on, fail, something's gonna fail. Oh, okay, and the wood itself failed here. The final fail strength was 280 kilograms. I decided to try reinforcing the ends of the joints, first with the ones I already broke and glued back together, just to make sure that would actually work. So these would be ready for retesting, except Marius pointed out there needs to be a hole drilled through here like this, where the clamping screw goes through, so I have to add that too because that potentially weakens the frame. 110, this is about where it failed before. Oh, I think it's starting to yield now. So it looks like those mortise and tenon joints are starting to pull apart now. And the force has dropped enough now that it's declared failed, and I'm pretty sure this is just pulling out here now. With both of the repaired reinforced ones failing at the joint or near the joint, I figured that was a good idea, so off camera I did the rest of them. So glue failed on this one, and it's just kind of popped out the edge here. So this is a double mortise and tenon joint which should have a lot more glue area. I expect this to be stronger. So this is now more than the bridle joint had, but it's definitely whoa! It's definitely starting to fail, I was going to say. And this one mostly failed in the wood, but you can see here it's a rather unfortunate grain orientation, and the reinforcement itself failed on this one too. And this second double mortise and tenon joint had an interesting failure. I'd say this hole in here definitely contributed. Next, the double bridle joint, or finger joint as Marius calls it, That one should be the strongest if the wood doesn't fail. Well, that's the strongest one so far. Looks like it might be failing around the hole here. Yes, there's definitely something opening up around the hole. The force has dropped enough that it's declared failed. 180 kilograms, but the peak was 202. Alright, Marius, here's my results. Weakest was the mortise and tenon joints pulling out. The bridle joints kind of split apart right here. Next was the double mortise and tenon joint. One failed around the hole. The other one split around at the reinforcement. And the finger joint, same thing. One split around the hole. And the other one split at the reinforcement. So the reinforcement wasn't big enough. Best were the plywood ones, but these ones I tested before I drilled this hole, and that hole is a cause of failure. So to make it fair, I made 2 more plywood joints, and both of these just kind of tear apart at the hole, and that made them the weakest, not the strongest. So the strongest joints were the double mortise and tenon joint and the finger joint, both being limited by the strength of the wood around the hole and the reinforced ends splitting apart.
Alright, thanks Matthias for breaking my stuff and the results. You should definitely check out his more detailed video about the testing. That's worth watching as well. I will now go with the double mortise and tenon joint, because that's easier to glue, and considering the amount, it's the best overall option. So let's start the production. The material is birch hardwood. Not the best choice, but I had some boards left over from a different project, which otherwise would have been burned. I milled them into strips and cut them to length. The joinery gets done with the Panther router and a custom template I made. This machine uses a router to copy the shape of the template to the workpiece. If you want to see this in more detail, check out my last video, but here's the workflow. With the follower in the slots of the template, I can cut the mortises. And with the follower around the slots, I can cut the tenons. The tapered shape of the template allows me to dial in the perfect fit. Alright, the C-frame construction is done. Gluing comes later because next I'll tackle the challenge of the clamping handle. On the commercial version they use a high-pitched trapezoidal screw and the threads cut into the frame. So low part count and 1 manufacturing step, about as good as it gets. And again, this is not really a feasible option for me. I'll be using M12 threaded rods because on a homemade bar clamp I used M10, which works pretty well, but I often wish to have the higher thread pitch to open and close the jaw more quickly. So another question is how to get M12 threads inside the wooden frame. One option would be to just cut the threads directly into the wood. And from a manufacturing standpoint, this would be ideal. Drill 1 hole, cut 1 thread, and it's done. But are these strong enough? This is about the handle size I'll be using. Let's try strip the threads with that. Going as hard as I can, both-handed, with gloves, the threads arrived. And let's be honest, this is a load the clamp will never see. So is it strong enough? Yes. But of course only until you go at it with a wrench. Something interesting just happened. I wanted to show the threads fail when you go at it with a wrench. But what actually failed first is the wood itself from the compression. If I thread in the screw from the other side, the threads are still mostly fine. But it definitely doesn't spin anymore. So let's go metal threads with a few options. Threaded inserts are expensive. T-nuts in M12 are almost as wide as the frame, and I don't like that. But the thin version of regular nuts seems fine, and I can cut hexagonal pockets with the Panther router. One on this side and one on this side. The 2 nuts are now kept in place, and this is obviously stronger and more durable than the wooden threads, but also more effort to make. I will still go with this solution for the simple reason that it works a lot smoother. And I want smoothly working clamp handles. On the Panther router, the stock needs to be centered, which I can achieve with the centering fence, and 2 more stops in the front. The template I made has 2 functions. By following the inner hole, I can cut the through hole for the spindle. And in the first run, I did this to all pieces. Then sliding the follower to the hexagonal part and set the depth stop. And from there it's just a plunge cut to depth, following the template around, and flip the part for the second side. All done in about an hour, except for some deburring. Nice. The nuts then get pressed in with the vise. Quite some repetition in this project. Now aligning the threads of the second nut with the first one when it's all the way in is basically a game of luck. And most of the time it will end up binding like this. So then I pull the nut back out, turn it by 60 degrees, push it back in and retry. On this one it seems like it already did the trick and now it spins freely. Doing this to all of them will take some time, and I will also remove the nuts again for painting the frames, so I will do all the alignment after painting. So now let's cut all the threaded rod to length and start working on the clamping pad. I want the pad to be metal on metal contact with the spindle, be relatively thin and never spin as I tighten it. On a commercial version they have a ball shape turned to the end and a matching shape in the pad. With lots of grease it can swivel and rotate freely, and the C-clip holds it together. Now I have a ball turning tool for the lathe, but it's not set up. A common solution is wedging a washer between locked nuts. I used it for my bar clamp, where it works great. But this is way too thick and bulky for this clamp. Requires 4 additional nuts per clamp, and the clamping pad is not even there yet. Bad solution here. But fastening a washer to the end in a way it can swivel, I think is the way to go. I first thought about a screw, but the solution I ended up with is better in every way. So at the lathe, I first cleaned up one side of each spindle, measured the current length, chucked it the other way, and turned it to length. Then turning a short section on the end to a pin. My target diameter is 5.3 millimeters, which isn't all that critical, because it only needs to fit an M5 washer with a little play. In production mode, I did all this with one roughing and one finishing pass. And wow, look at that surface finish. Then cleaning up the shoulder with a little undercut and a chamfer with an outside chamfer tool. Now the washer will be the metal on metal and swivel part. And to secure it in place, I hit the end with a hammer all around, which deforms the metal, and the washer is now captive. I like the solution so much because it's easy and requires 0 parts. Probably also the reason why manufacturers do more or less the same thing. The actual clamping pad, I made a solid 3D print that has a pretty snug snap-on fit onto the washer. It's a one-time assembly. Trying to separate them will break the part, which is okay, because unless it breaks, the part never has to come off again. And so it's the same idea as before, low part count, minimal assembly time. Doing all that work is also a good practice for your death stare. Let's check the printer. Oh great, still 16 hours to go. Okay, so then let's make the clamp handles in the meantime. Together with the frame parts, I also milled down stock for the handles and cut them to length. I find their center, put them in my magnetic drill press vise, align it, and lock the magnet. What comes now may seem strange at first, but stay with me. I'm drilling a hole about 50 millimeters deep and then tap it M12. I finished the threads of this blind hole with the drill because my hand has a good sense of reaching the bottom and letting go. And here one of the spindles can now thread all the way in. And I did it like that because with just a 12mm hole, the spindle always still had some slop, which I didn't want. Sloppy and perfectly tight. And for actually transferring the force into the spindle, there will be a cross pin, which I'll also do later after painting. But the handle shape is far from done. First, I chamfered the ends at the table saw and the edges on the router table, or just by magic. And then I used a flap sander at max drill press speed to smooth out all edges. Quite a difference. Ah, the printer is done. Except for the cross pin, this part of the clamp is done. But what about these tabs? They will ride along 2 slots in the frame, which prevents them from spinning. However, on the actual pieces, there are no slots yet. Let's fix that. One cut from each side makes a perfectly centered slot. Alright, and now the most difficult but also most interesting part, the eccentric cams that make the clamp auto-adjust to any thickness. Well, actually, it's not eccentric, but a spiral curve. But besides the shape, it also needs to have a very grippy, preferably rubberized edge. It needs to be spring-loaded, so it comes back to a neutral position. And it also needs to have an end stop. There's a lot going on. The most difficult part will be the spring loading, so let's get that sorted first. On here, they used a steel torsion spring, pretty stiff one. But that's not a part you can just buy. So my first attempts were using rubber bands, or actually tiny O-rings. One end would be fixed in place in a channel in the cam, the other end to the frame, and then as you rotate it, the rubber band gets wrapped around the center. And as you can see, this looked pretty promising and worked well. Well, these are all the prototypes I made before that didn't work. But there's this one fatal flaw. After about 20 to 50 cycles, the O-ring would always snap. And unfortunately, this just doesn't work. So guess who bought some spring steel wire and has a task ahead of himself? My first attempts were definitely experimental. Some research later, well, a This Old Tony video, I knew I needed some tooling. Okay. I filed a flat spot onto a shaft to drill and tap a hole, which is then used to clamp the wire. This goes in the drill press chuck, and with the belts and speed set slow, I gave it a go. Well, shit. Let's try again. That's not bad. Okay, now it's bad. Well, at least it's a coil. Sort of. 3 times the charm. Ah, that's what I wanted to see. Nice tight coils. And the spring is a bit less garbage. I think I need a better way of feeding the wire. So I cut another flat spot to some brass stock, then cleaned the face and the diameter just to get that sexy footage, cut it off and drilled a tiny through hole. At the flat spot I cut some more threads for this brass screw. All this goes in the vise. The wire comes through the hole and the screw clamps it to create consistent tension. And here we go. Oh great, much better results. Ah, forget it. Well, let's try the wire feeder closer. Ah, shit. Great, another one of these. Okay, now we're getting results. Better, but not consistent yet. I have to make over 60 identical springs, and looking at the results so far, I can't see myself doing it that way. Let's try something else. Would you look at that? Good and consistent results. And it was easy. Shout out to the Thespringguy whose method I basically just copied. Let me show you. The tool I use here is my wood lathe with a chuck and a drill bit. The belt is removed and a makeshift hand crank attached to the end. A drill would work exactly the same. The hand crank is just easier to handle. Now the magic behind all this is this wire catching hook made from the same spring steel wire. And making it is quite simple. Start with a drill bit in the chuck, loosely put a wire inside the chuck jaws and start coiling. The coil will spring back and then find a bigger drill bit that's a hair too big and push the coil on that. Back in the chuck, take a short piece of the same wire and bend the open end around it. Then close it all the way and cut off the excess to create the hook. Shorten the other side and it's done. It's such a beautifully simple concept as it clamps itself onto the drill bit and will never slip. Okay, so now I can consistently wind springs, also in different size. Now I need to figure out what's the right size and the amount of windings and how to mount the springs to work in the clamps. So to start somewhere, I took one of the sample springs, bent a hook to one end and this to the other end. Then made a matching cam on the CNC router. The hook fits into this hole and the rest of the spring around the center. And this end fits into a hole on my test block. Let's see, this is the neutral position and it works. Really? First try? No way. But yeah, that's exactly what I need. I'll take it. So that would be 1, 2, 3 windings with the diameter this setup produced, and I'm pretty confident the hooks and holes also work. But can I also assemble it? Long end goes into a hole in the frame, hook into the hole in the cam, and I can get it in. Oh yeah, it works. As you can see, I've done a bunch more testing trying to make the ideal spring, varying the amount of windings, and I also went up to a thicker 0.7mm wire diameter to get them a bit stiffer. But what it all came down to in the end was, can I assemble it? Take a look. This spring with the hooks next to each other is super simple to assemble, but puts the cam in an awkward starting position about here. So I have to pre-tension it all the way to here to get it to clamp neutral, and then it doesn't have enough travel. This spring with hooks on opposite ends puts the cam in a perfect neutral position about here, but it's so hard to assemble, there's no way I'm doing that for all of the clamps. So the solution is an in-between spring that has the advantages of the other two, and I've already got it installed here. Oh, I like that. And it also already has the stop included. We'll get to that. Now I have to make more springs. The hooks I made by bending over the ends with some round tip pliers, then pinching the bend a bit more and cut off the excess. And there I've got all the springs made, but they aren't of much use without all the features in the frame pieces. And that is drilling the hole for the pin and adding a chamfer. Then drilling the hole for the spring and stop feature and adding a chamfer. By the way, every operation has its own setup. The roundover starts at the bandsaw, gets finished at the belt sander, and adding a chamfer. Now adding reinforcement splines Matthias recommended. The bandsaw curve is ideal for the spline thickness. Then cutting matching splines to thickness and length, and with glue on every surface I can push and clamp them in place. Afterwards I of course have to flush trim and drill through all holes again, and now finally making the big cutouts for the cams. I built a jig for the table saw to hold the pieces securely, aligned the sawtooth with my mark, and made 2 cuts. The middle gets removed at the bandsaw. It took a couple attempts to get the amount of plate just right, but then it went rather quickly. On top of removing the middle, I set up the fence and the stop block to clean that bottom surface with the side of the blade. A noticeable difference. Most of the new edges I could then chamfer with the router and the rest with the flap sander. And with that, all of the part features are done and they are ready to be glued. Now the effort of making the double mortise and tenon pays off, because all I need to do is spread glue in the mortises and on the tenons, then push and clamp them together, remove the glue squeeze out, and it's done. No need to check for square or deal with a big glue mess, and once fully pushed, no further clamping is needed, I can just let them dry like this. While the glue is drying, I can cut the cams on the CNC router, which is boring to watch, so here are the interesting bits. I use a good amount of bolts and T-nuts to hold the stalk to the table. To locate it on the wasteboard, I have a pin in my hole grid that will fit this hole, which puts it in the same spot as in my software. And then I load the program and start the job. Yeah, boring, except for the automatic tool changes. The last operation is flattening everything to thickness, and that's why I've sunken the bolts below the surface. I also optimized the tool paths in a way so when the job is done, I'm left with clean and sharp edges everywhere. And I made 3 of them. For the other side, I machine another locating hole into my wasteboard. Let's call it friction milling. Oops. But now I could use the hole from before and one of the machined ones for locating. Here I also managed to prevent tear out by first machining a slight chamfer and then the contour. Then I cut the parts free, flush trim the holding tabs and take care of all sharp edges. I enjoyed making these cams so much that I thought, let's screw up the geometry and do it all over. The grippy stuff on here seems like some kind of rubber silicone material and also looks like being cast in place. Surprise, surprise, I can't do that. The best alternative I could find is this solid rubber edging material. Car tire. I posted this on Instagram and got quite funny responses from you. I guess these jigs for cutting and chamfering the rubber need no explanation, but for better glue adhesion, I scratched the surface with 60 grit, cleaned it, and applied the glue. It's one of those contact type glues that you spread to both surfaces, then wait, and then press them together. I did that by kind of rolling it on while keeping it straight. One end gets secured with a staple, the other with a little nail, being careful to miss the hole. By now, the glue in the frames is bone dry, so I cut off the corners and sand over all sharp edges before applying a finish. I like the look of this hammered finish, however, I have never used it before and it's not specifically made for spraying. But then they also sell this stuff in spray cans, so why not? A simple dowel gives me perfect access to all sides. And what can I say? Spraying went wonderful. Then picking the parts up with a wire and hang them for drying. This is the result after 2 coats. What a success! The clamp handles I could partially thread on the spindles, spray them red, and they already have a hanging device built in. Pretty cool. With the paint dry, I sanded the raised grain of the inner surfaces so the cams don't rub on it, and then tapped the countersink holes for the stopping screws. And now I'm ready for the final assembly. First, the 2 nuts where I now make sure they are aligned to each other and spin freely. Then threading in the spindle with the clamping pad and thread on the handle. Now 2 cams, springs, pins and screws. Installing the spring is still fiddly, but works. And with the tiny amount of paint in the holes, the pin now is a good press fit. And now the stopping screw. The end of the screw rides in this track. This end stops it at the neutral position, and this end limits the max opening and prevents the spring from damage. Then the other side, and repeat the whole procedure 30 more times. The threads and the pads then got some grease, and after the last operation at the drill press, where I drilled a hole for the cross pin, they are all done. That was a journey, and this one is already damaged. Well, that's because I've visited Stefan from CNC Kitchen and his load cell. There we could test what my clamps can actually push. The clamp grips on a material sample and pushes the 2 levers together, which are connected to the load cell. I've used a torque wrench for a consistent and reasonable force that I would also apply by hand, and that doesn't damage anything. The screen then shows the force, which, because of the lever, needs to be doubled, and I converted it to kilograms, which is easier to grasp. And like this, I tested hardwood, softwood, plywood, particle board, plastic, and finished wood. What's also happening is that once the max force is reached, it slowly decreases again and eventually settles. Overall, not spectacular, so I brought 1 clamp to sacrifice and pushed it to the limit, which turned out to be the rubber. 63 kilograms, however, is still impressive. But what about the commercial one? It crushed through this test, going over 200 kilograms until the test levers broke. And I took them to the face. But thank you, Stefan, I will remember. Stop looking at it. Now let's use the clamps as intended. So glue goes on, then the edge, and then the clamps as you'd expect. When I use the clamps normally like this, and everything has settled, that's like having a 20 kilogram weight every 10 centimeters. And that's plenty to glue on an edge. And now it's 5 days later and the clamps are still tight. They didn't slide themselves loose. Excellent. This project is a total success. One question remaining, are they any better than these? In terms of overall performance and quality, obviously no. But I made them more user-friendly. Take a look. From the shape, you would intuitively think you can just slide them onto a workpiece, and that works for thinner stuff, but not for thicker stuff. And my clamps aren't any better. So you have to manually open the cams, slide it on, and same for sliding off. That's awkward. It's the same on mine, but I integrated these tabs for your fingers, and they make this easy. Quite important feature, I think. And they are also easy to store, because I built them flat and stackable to nicely fit in a box or drawer. If you want to win 5 of the clamps, just leave a standalone comment saying, I want the clamps. If you want to comment more than that, make this a separate comment. This will be easier, because in a week I will randomly draw one of the I want the clamps comments and try to contact you by answering to that. Also, check the video description. And last surprise, next weekend Matthias and I will host a live stream together where we watch this video together and pause at certain moments to give you more details and behind the scenes stuff, while also doing a live Q&A. So it will be kind of an experiment for both of us, and I hope to see you there.